Greetings of the day, welcome back. So today I am going to talk about the Mohr circle diagram for plane two-dimensional stress system. So elements subjected to two-dimensional stress sigma x, sigma y and tau xy, the general two-dimensional stress system. So to do that, to understand how the Mohr circle diagram is analyzed, so before that we need to understand the mathematics behind it. So we have taken two equations, so equation 1 and equation 2. Equation 1 is a normal stress which is used to find a normal stress on any inclined plane. So sigma x, sigma y by 2 plus sigma x minus sigma y by 2 times cos 2 theta, tau xy times sin 2 theta. So here sigma x is the stress acting on x direction on a two-dimensional element. So in the y direction, and tau xy is the shear stress acting on the same element. And theta is the inclination of the plane in which we are finding the maximum and minimum principal stresses. So similarly, this equation sigma t gives the shear stress acting on the plane which is inclined at the same angle theta. So we are taking this equation 1 and equation 2 and we simplify the equation 1. So taking this equation, I have taken this part to the left hand side, so that sigma x minus of this sigma x plus sigma y by 2 is equal to the remaining equation of the equation 1. So that I am calling as equation 3. Now squaring and adding equation 2 and equation 3, the left hand side is squared and added and right hand side squared and added separately. So squaring this part, we get, squaring equation 2 and 3. So this is equation 3. Now squared this part, that is sigma x minus sigma x plus sigma y by 2 whole square. This part is square. Again left hand side of equation 2, that is sigma t square is equal to, again square and add the right hand side of equation 2 and equation 3. So equation 3, sigma x minus sigma y by 2 cos 2 theta, sigma x minus sigma y by 2 square cos square theta, because we have to square and add. So squaring this term tau xy square and sin square 2 theta. Now the right hand side part of the equation 2, square this sigma x minus sigma y by 2 whole square times cos square 2 theta, plus again square and square this part, minus of tau xy is tau xy square, square, minus into minus plus, so that way it is tau xy square here and cos 2 theta whole square. So this squared and added part of the equation 2 and 3. Now we will further simplify this equation. So this is done as it is. So here if you see this simplified equation, so this term and this term is having common. So there is sigma x minus sigma y by 2 whole square. Sigma x, this is supposed to be minus. This is supposed to be minus. This is minus. Both terms are minus. So this term and this term is same. So take the common term from this. So taking the common term, we can write sigma x minus sigma y by 2 whole square. So that you take common. So when you take these two terms common, you will have cos square 2 theta and sin square 2 theta. So cos square 2 theta, sin square 2 theta is equal to 1. So that way, so you will left with only sigma x minus sigma y by 2 whole square. So coming to the next term, that is this. So tau xy square times sin square 2 theta and tau xy square cos square 2 theta. Again tau xy is a common term. So take this common term. If you take this common, again you will have sin square 2 theta plus cos square 2 theta. Again sin square 2 theta plus cos square 2 theta is equal to 1. So you will left out with only tau xy whole square. Now this equation is a simplified form of the previous one. So if we rewrite this equation like this, sigma n minus a whole square, sigma n, this I am calling as a, sigma n minus a whole square plus sigma t as it is. So this I am calling it as a r, which is the radius of the Mohr circle in fact. So here I have written, so a is equal to sigma x plus sigma y by 2 and r is equal to this. So here in this equation actually is A is equal to sigma x plus sigma y by 2, which is called the average stress, which directly gives the center of a Mohr circle, and this r gives the radius of a Mohr circle. So let us recall the general equation of a circle. So this is the general equation of the circle. So x minus a whole square plus y minus b whole square is equal to r square. So here recall A and B represents the intersection of the center, the center of a circle, and XY are the coordinate point on a circle, circumference of a circle, and R is the radius of a circle. So it is written here, A and B are the center of a circle, R is the radius of a circle, and XY are the coordinates. That means, so this equation is the basis for the Mohr circle diagram. That means if you understand this, understanding the Mohr circle diagram and its meaning is very important. So we will understand the construction of the Mohr circle through an example. So let us consider a two-dimensional stress element. The two-dimensional element subjected to a sigma x, that is normal stress acting in x direction, and again a normal stress acting in y direction. So both are tensile in nature, and it is subjected to the shear stress acting in all the planes. So like this, so tau xy is the shear stress. So in order to draw the Mohr circle diagram, we need to find out the coordinates of x phase and y phase. The coordinates means the stresses acting on the x phase and y phase. So here I have written, consider this as x phase, and this phase is considered as y phase. So the stresses acting on x phase are sigma x and tau xy. The stresses acting on y phase are sigma y and tau xy. So you know the sign convention for the normal stress. If the stress is acting away from the body, which is considered as tensile, and it is positive. If the stress is acting towards the body, it is compressive stress, and the sign convention of that is negative. So positive, negative directly you can take for the normal stresses. But what is the sign convention for the shear stress? That is very important. So this shear stress, which is acting in the clockwise direction in this phase, so is considered as positive, and the shear stress acting in this phase is counterclockwise with respect to this. It is counterclockwise, so it is considered as negative. So the clockwise shear stress is considered as positive, and counterclockwise stress is considered as negative. But how do you remember this clockwise shear stress and counterclockwise shear stress? It is easy to remember if you remember this situation. So in a living hall, so where do you keep the clock? So usually you keep the clock in the wall, that is above, and where do you keep the counter? Usually keep the counter on the table. So wall means above, counter means below. So above is considered as positive, below is considered as negative. So what is this above and below? See, it is with respect to this coordinate system. So above this positive, below this negative. So remember, above positive, below negative. So with respect to that, so this is the clockwise shear stress, clack above positive. So this is the counterclockwise shear stress, counter below, so negative. So if you write the sign convention of one shear stress, other one will be obviously opposite to it. So if you write one, other one you did not check, straight away you write the opposite sign. So sigma means the x phase coordinates and y phase coordinates are written like this. So now this x phase coordinates and y phase coordinates have to be reproduced onto a Cartesian coordinate system with the proper sign convention. So because the Cartesian coordinate system will have the coordinates to be, for example, this is the first quadrant, all the values here are positive, so we write in the form of plus x and plus y. So this is the second quadrant, this is the second quadrant, so the coordinates in this quadrant will be of the form minus x plus y. So here this is third quadrant, minus x plus y minus x, minus x minus y minus x minus y, and coordinates in the fourth quadrant will be of the form plus x minus y, plus x minus. That means if you remember this sign convention, so you can easily locate these coordinates on a Cartesian coordinate system. So here I have taken first an example, then we will explain once again with the proper example so that the concepts are very clear. So now, these x coordinates are represented here. So this is what is the sigma x distance, and this is what is tau xy distance. So plus sigma x plus tau xy. So these values are represented here. Initially, what we do is first we locate a point in the Cartesian coordinate system. That means we are located, let us assume that we have located the point x here. Similarly, locate the point y. The point y is here. So y is, this distance is sigma y, and this distance is tau xy. Just locate this point. So after locating the points x and y coordinates, you join them. So draw a line from here to here. So actually the xy is actually the radius of the xy is a diameter of a Mohr circle. So this xy diameter will intersect with the x-axis, that is at point C. Now taking point C as center, CX as radius, you draw the circle. So after drawing the circle, what you get is a Mohr circle. Okay. Now the intersection of this Mohr circle with the x-axis, that is sigma axis, is important. So that will give you the maximum and minimum principal stress. The farthest intersection of the Mohr circle with the x-axis is what is considered as sigma 1. Actually, this point here is sigma 1. So from where to where you will measure? You measure from O to A to the scale. You measure from here to here. Then where is point 2, that is minimum principal stress? So the nearest intersection to the origin is what is known as the minimum principal stress. Okay, you measure this distance to the scale, you will get sigma 2. Then what is the maximum shear stress? You know, in the previous understanding we understood, previous theory we understood that the radius of the Mohr circle gives you directly the shear stress. That means R is equal to, you recall the previous equation, so R was equal to under the root sigma x minus sigma y by 2 whole square plus tau xy square. So this will directly give the radius of a Mohr circle. So you don't need to worry about this mathematical equation. So directly straight away measure this radius, that will give you tau xy. That means the distance from this to this. This is actually tau xy. This is tau max actually, not tau xy. Maximum shear stress. The distance from here to here is sigma minimum. That is the minimum principal stress. The distance from here to here is sigma maximum, or is also denoted as sigma 1. Most of the cases this is standard notation. This is sigma 2. Okay. So now from this Mohr cycle diagram, we could able to measure the maximum principal stress, the minimum principal stress, the maximum shear stress. Also, it is possible to measure the direction of the direction of the plane in which the stresses are maximum. So the inclination of the plane. So inclination of the plane will be measured with respect to this xy plane. So usually with respect to point x and the sigma axis, the angle will be measured. So this is the angle. So this plane to the sigma axis. So this 2 theta. So direction will be in which direction, if you rotate the plane x, that will merge with sigma axis. So that is the direction. So here I have written direction, that is clockwise direction. So if you rotate this plane x in the clockwise direction, so this will merge with sigma axis. So that is the direction for the plane where your stresses will be maximum. Yeah, from this Mohr circle diagram, you should be able to calculate the radius of a Mohr circle. So please remember, radius of a Mohr circle gives the maximum shear stress. That means, so this CD, CX, CY, CA, CB, so all are giving you the radius of a Mohr circle. Now, how we can find the radius of a Mohr circle? But we already know that radius of a Mohr circle is equal to tau max. But how do we prove it geometrically using this equation? So let us see. So we know CA is equal to CX is equal to R. CA is equal to CX. All are radius. So that is equal to R. So now from the triangle CFX, which is the triangle CFX. So CFX is a right angle triangle. So this is 90 degree and this is 2 theta. So from the triangle CFX and from the Pythagoras theorem, we write CX square is equal to CF square plus FX square. So Cx square is equal to Cf square plus Fx square. So what is Cf? Cf is this distance. So how do you find this distance? How do you relate this distance in terms of the known stresses, that is sigma x, sigma y and tau xy? So let me see here. So the distance from here to here is sigma x. This distance is sigma x. And the distance from here to here, the distance from here to here will give you the center of the Mohr circle. The distance from here to here gives you sigma y. That means if you know this distance, half of this distance will be CF, because the distance of the tau xy will be same from the horizontal axis. So what we are doing, we are taking sigma x minus sigma y, so that you will get this distance, half of that, that is OF. OF, which is sigma x, minus OG, which is sigma y, by 2, because we want half of this distance, so by 2. So by 2 plus fx square, as it is, right? So OF is sigma x, OG is sigma y by 2. This is square. This is square. So plus fx is fx is tau x square. So this distance is tau xy, tau xy, not xy square. The distance is tau xy. So tau xy square. So if you see this equation, because it was exactly similar to r, that is radius of the Mohr circle. So Ca is equal to r square. Or if you want r, this is the root of this. The root of sigma x minus sigma y by 2 whole square plus tau xy square. So now we use this relation to find out the maximum and minimum principal stresses. So now from the Mohr circle diagram, how do we find out the maximum principal stress? See, I have already told maximum principal stress is the distance from O to A. The minimum principal stress is the distance from O to B. So from this geometry, we should be able to calculate the maximum and minimum principal stresses. So after you construct this in a graph sheet, you can just directly measure it. Just measure it, measure the distance O to A. That's all. To find the minimum principal stress, just measure the distance O to B. But one thing that you must ensure while constructing Mohr circle diagram is that the scale of x and y must be same. That means if you are taking 10 MPa is equal to 1 centimeter, the same 10 MPa is equal to 1 centimeter you have taken y direction also. So if you take different scales for x and y direction, you will not get the Mohr circle diagram. So because you have drawn this to the scale, you can try to measure the distance OA and OB, and obviously CD and all that. However, it is possible to derive the analytical equations from this Mohr circle diagram. So here we will see how we can get the equations for maximum principal stress, minimum principal stress and shear stress. So you see the equation sigma 1. So sigma 1 is equal to OA. Refer the diagram there. Sigma 1 is equal to OA. So this OA is equal to OC plus CA. What is OC? OC is this OC plus CA. So OC is what? Recall OC. What is OC? OC is the center of the Mohr circle. So while doing the derivation, I told center of the Mohr circle is equal to the average shear stress. Average normal stress, that is sigma x plus sigma y by 2. So OC is equal to sigma x plus sigma y by 2. So substituting OC is equal to sigma x plus sigma y by 2. And what is CA? CA is the radius of the Mohr circle. So straight away CA is written, which was derived in this equation. So straight away it is written. And this, you recall this equation which was derived analytically. So using the for a two-dimensional stress system, so that we directly got from the simple circle. So similarly, for the minimum principal stress also we do. So minimum principal stress, that is sigma 2 is equal to OB, this distance. So how do you find this distance from the geometry? You see here. So if you know OC, OC is the center of the Mohr circle. So if you know OC, from the OC, if you subtract the radius, you will get this distance. That is what is required for sigma 2. See, from the OC, if you subtract CB, you will get this distance, right? So geometry, from the geometry it is OC minus CB. So OC is what? OC is the center of a Mohr circle. Then what is CB? CB is the radius of a Mohr circle. So center of the Mohr circle, sigma x plus sigma y by 2 minus radius of a Mohr circle. So this equation. So you recall this equation which was derived analytically, which gives the minimum principal stress. So this I did not explain again because it was explained earlier. So the radius of a Mohr circle directly gives you the maximum shear stress. Now coming to the determination of the angle of the plane where the stresses are maximum and minimum. So we use the triangle CFX, which is the triangle, this triangle CFX, which is again a right angle triangle. So from this right angle triangle, we are writing tan 2 theta. So tan 2 theta is equal to, from the diagram it is vertical by base. So vertical is Fx, y by x, yes. So this is the vertical Fx and this is the base. So this distance by this distance. So it is Fx by Cf. So Fx is this distance. This is Fx and this is Cf. So what is Fx? This is Fx. So Fx is equal to the shear stress tau xy. Then what is CF? CF you can find if you know OF minus OG, you will get FG by 2. If you do, you will get CF. That means O to X or O to F, this distance minus this distance. If you do this distance, you will get half of that distance will be this, right? So it is OF. So straight away it is written here. However, that is how it has to be calculated. So OF means O sigma x minus sigma y by 2. That's what is equal to OF minus OG by 2. That is what is this equation. So after simplification, you will get tan 2 theta equation. So in this equation we can find out the plane in which the stresses are maximum. To understand the Mohr circle in detail, let us solve one numerical example. So in this numerical example, so this is a two-dimensional stress element subjected to two normal stresses. So 40 MPa tensile, 30 MPa tensile, and the shear stress 40 MPa. So EM is like this. So given this, in this stress element, we need to find out the direction, magnitude and direction of the principal stresses. That is, we have to find out sigma 1, magnitude is sigma 1, and you have to find out sigma 2, this is the magnitude, and direction. So direction is tan 2 theta. We have to find out tan 2 theta, that is the first one. Second one, direction and magnitude of the shear stress. You have to find out tau max. Okay, so direction of this we will see later. Now for this problem, so how do we solve? So to solve this problem by a graphical method we are solving. So by graphical method means the Mohr circle diagram method. So to solve it by Mohr circle diagram, you need to identify the coordinates of the Mohr circle. So as already discussed in the previous lecture, so this face is considered as the x face and this face is considered as y face. So your aim is to just write the coordinates of the x face. So where do we write? So let's write here. So if I write here, so x is equal to, in the form of sigma x tau xy, x comma format. So this is x, this is y. So this is 40 plus 40 because it is a positive normal stress. And what is the sign convention of this? See, this is the shear stress acting in the counterclockwise direction. Counter means, please recall the sign convention which I told earlier. Counter means below. So it's supposed to be minus 40. Okay. Now come to the y phase. So in the y phase, this is y phase. In the y phase, again in the form of x comma y or sigma comma tau xy format. So this is sigma and this is tau xy. So what is the sign convention for the sigma? It is a tensile stress, so it is positive plus 30, and other one will be obviously positive. So don't need to cross check it. So straight away we can write plus 30 comma plus how much? 40. So just locate these coordinates in a rectangular Cartesian coordinate system. So Cartesian coordinate system means you have to draw this on a graph sheet. So take the graph sheet. In the graph sheet, you locate the axis like this. Tau, this is sigma axis. This is plus sigma, and this is minus sigma, and this is plus tau, and this is minus tau. Okay. So divide, mark the coordinates, mark the points. So in graph sheet you can directly mark. Make sure this scale and this scale is equal. Okay. So you have to mark you have marked. But what is the scale you take? Scale is very, very important. What is the scale? See, this 40 MPa stress you are representing on a linear scale. So you require scale. So how much we take? Say for example, let us say 10 MPa is equal to 1 centimeter. So this is the scale I am taking. So you can change it. So 10 MPa is equal to 1 for both x and y. That is very important. You cannot change the scale for x axis and y axis. So for both it is same. So to represent the x coordinate, x 40 and y minus 40. This is x, sigma means x axis, tau means y axis. So 40. So 1 centimeter I have taken 10 MPa. 10, 20, 30, 40. Here also 40, but in the negative minus 40. So minus 40 will come here. So 10, 20, 30, 40. So take this 10, 20, 30, 40. So which is this point? This is point X. This is point X. Now you have to locate point Y. So how do you locate point Y? 33 units along X direction and 4 units along Y direction. So both are positive. Both are positive means that will come in the first quadrant. So X 30, 10, 20, 30 and Y 40, 10, 20, 30, 40. So we write 30, 10, 20, 30, 40. This intersection. So which is this point? This point is Y. Okay. Now join X to Y by a straight line. Okay. You have just joined X to Y. Now the intersection of this diameter with the sigma axis is what is considered as the point C, the center of a Mohr circle. And this is the origin. Taking this point C as center, Cy or Cx as radius, you draw the circle. Take this point as center and draw the circle. So we don't know where it exactly intersect because I have not taken this to the scale. If you draw exactly to the scale, you will get the exact circle and exact intersection. So this is an arbitrary representation. So approximately in this diagram, this point gives you point A and this point gives point B, means this is the maximum principal stress and this is the minimum principal stress. Remember, the direction of maximum principal stress and minimum principal stress are separated by 180 degree. So the sigma 1 and sigma 2 are in straight line, that means 180 degree in terms of 2 theta. So in terms of theta, there will be 90 degree. Now that is what is sigma 1 and sigma 2. Then where is tau, that is the maximum shear stress. From the center C, you draw a vertical line. Okay. So this is what is tau max. Tau max. So let this point be D. Okay. Now to measure the distances, directly you can straight away you can measure. Say sigma 1 is equal to, what is sigma 1? Is the maximum principal stress. It is from O to A. So O to A. You take any linear scale and just measure it directly. That's no need of conventional thing. So if it is, for example, 10, 20, 30, 40, 50, 60, 70, around 72 MPa. So this is not exact solution, approximate solution. If you do it on a graph sheet, exact solutions you will get. So approximately with respect to this diagram, it is around 72 MPa. Then what is the minimum principal stress? Minimum principal stress is here. So in this diagram, so this intersection is taking place in the negative axis. So this would be approximately -2 or approximately, so it is -2 or -3 MPa. So sigma 2 will be the distance O to B. It is O to B. So if this B is taking, if the B point is in the negative side, this axis, then it will be negative. If this point B is right hand side of O, then this will be positive. So because it is an approximated circle, so with respect to this diagram, it will be, so I will write approximately. So this will be approximately say -3 MPa. So we could measure sigma 1, sigma 2. Then how do you measure tau max? See, tau max is directly the radius of a Mohr circle. So straight away measure the radius of a Mohr circle anywhere in the diagram, and that gives you the stress directly. So we could able to measure sigma 1, sigma 2 and tau max. That is magnitude of sigma 1, sigma 2, tau max we have determined. Then what is the direction of you have to find? So to find the direction, analytically we use this equation, tan 2 theta is equal to 2 times of tau xy divided by sigma x minus sigma y. But practically, graphically, so we can straight away measure the inclination of the cx with respect to the point cx. If you project this, cx is in the this side, say fourth quadrant. So angle 2 theta will be this. So how do we take the direction? In which direction? If you rotate the plane x, that will merge with sigma axis. So that is the angle. That means here, from here to here is the angle 2 theta, and direction will be the same direction how we are rotating. So approximately you will get say 85 around. So this is around. So what you are measuring is directly the angle, say 88 degree. So what I have measured is just approximately based on this diagram, I am giving you the answer. So in the graphical, in the graph sheet, directly measure this angle using protractor. So that gives you directly the angle. Okay, then while showing the stresses, direction of all these stresses, you have to show them an element. So to show the element, show the stresses and directions on an element, you construct an element. So this is the plane of sigma x, this is the plane of sigma x, not the direction. So this is the plane of sigma y. Okay. Now in order to show the maximum principal stress sigma 1, we have to measure, we have to locate this angle. Right? So this was 88 degree approximately in terms of 2 theta. While reproducing this angle and to the 2-dimensional element, you have to take half of that because we need theta. So if it was approximately 88 degree, take half of that. So around 44 degree. So from the plane of sigma x, in which direction you measure the angle, in the same direction you rotate the element or you draw a line. So it is approximately 44 degree. So 44 degree somewhat like this. 44 degree in which direction? The same direction how you measure. The paint here this way. This is theta. On this plane, the maximum principal stresses will be shown. So this is what is sigma 1. So how much ever you got here, sigma 1, you have to just show that. If you have got a positive value, you have to show tensile direction. If you got a negative value, you have to show the compressive direction. Then the sigma 2 will be perpendicular to the direction of sigma 1. So perpendicular to this plane. This is 90 degree. Perpendicular to this plane, draw the another plane where the minimum principal stress exists. So this is the direction of minimum principal stress. I am giving compression direction to this because in my calculation I got minus 3 MPa. So this is what is sigma 2. Then shear stress will be 45 degree to both of these planes. That means this angle is 45 degree. Even this is also 45. And shear stresses will act because shear stress will act along the plane. So this is drawn parallel to this. So here we will show the turbines. Okay. So with this we have calculated maximum principal stress, minimum principal stress, maximum shear stress, and their direction. So directions are this. So whatever we have shown is theta 44 degree, 45 degree, 45 degree, 90 degree. So these represent the direction of the maximum principal stresses, minimum principal stress, and shear stress. So with this we could complete the problem.